All right, we're going to talk about transformers. So for transformers, there are several flavors. One flavor is voltage step down and current step up. And this particular type is most typical. Then we also have voltage step up and, oh darn, it just did that, didn't it? Please. Okay, and step current step down. And these are often for, now let's go here, our international friends laptops. Then you have a unity transformer, and that's used for isolation on test benches. Okay. Now, then there are also multiple secondary transformers. And your multiple secondary transformers provide multiple secondary voltages. These are commonly found in computer chassis power supplies. Okay, now that's good. Now I'm going to go ahead and draw some things on here. Draw. Yeah, let's bring in a pen. We've already spent some time last time. I'm going to take off the keyboard. We spent some time last time working out a voltage step up and a voltage step down transformer. I'd like to spend a few minutes with you to talk about multiple secondaries. And multiple secondaries will look like this. I will have a primary and here, and I will have a secondary, and I will have another secondary. And so I can have, in this particular one, this would be my V1. This one would be my V2, and this will be my V3, if you will. And the turns ratios may go something like this. Let's say I happen to have 16 over this side, and put in a colon, and that's to 3. And then over here, I happen to have a 14 to 5. And if I say that I happen to have 120 volts, and that's RMS, and I'll go ahead and put in a load in here. Let's take a look and see. Yeah, that's fine. Erase. I'll go ahead and put in a load here and put in another load here. And let's say RL1 is equal to 560 ohms. And I'm going to say RL2 is equal to 470 ohms. Okay, so you're going to be tasked with finding several things. You're going to be tasked with finding the following. Determine V2, I2, V3, I3, P2, P3, and let's see, that's good. Let's go ahead and play with this and see how it is, how we do on this. Okay. So if we're going to play with the upper secondary, we have a 16:3 ratio, yes? So remember our transformer formulas. Transformer formulas are given as this. V1 over V2 equals N1 over N2 equals I2 over I1. Now, because there's a multiple secondary, we can also say this. We could say V1 over V3 is equal to N1 over N3 is equal to I3 over I1. So those would be your appropriate formulas for each of the secondaries. Now let's go ahead and see if we can determine what's happening in the upper secondary. So everybody get your calculators out. Do some calculations. I'll be calling out on names. And how do I set up finding my V2? The question goes to Wei Ji. How do I set that up? How do I find my V2?
You use V1 divided by, we use N1 divided by N2 first, and then we use the V1 divided by the result.
Yeah, so we happen to have N1 over N2. We're going to use this part of the formula, yes, what I've outlined in red. Everybody see that? I have V1 over V2 equals N1 over N2. And so if I go to do the math on that, my V1 over V2 equals N1 over N2, and that will be equal to 120 over V2 is equal to, so what's my N1 over N2, Wei Ji?
16 over 3.
16 over 3. Is everybody clear on how we set that up? We just follow the formula. We have two ratios. We have one unknown. So how do we solve this? We cross multiply, yes? So you cross multiply. So this works out to be 360 equals 16 times V2, yes? And so how do I solve for V2? I simply divide both sides by 16. And so my V2 works out to be 360 divide by 16. So Wei Ji, what do you calculate?
22.5.
So we end up with 22.5 volts RMS. Are we okay with determining V2? Everybody okay with that calculation? Yeah. All right. Now, once we have the V2 calculation, we need to determine I2. So we've already got the V2. We'll just put a box around it. Now we're looking for I2. What method do we use to find I2? Robert, how do I find I2, the current going through I2? The current in the upper secondary. How do I find that?
Not sure.
Well, take a look at what we just calculated. What we just calculated is V2, and that's up here. We just calculated 22.5 VRMS. And I gave you the load resistor. The load resistor for the upper secondary is 560 ohms. So again, so how do I find that current in that upper secondary, I2? Ohm's law, sure. Ohm's law says you got to have some kind of a V over some kind of an R, yes? Which V are we going to use? V2. Which R are we going to use? RL1. And so this works out to be 22.5 VRMS. And this is going to be divided by 560 ohms. So Let's go ahead, hit our divide key by 560. And Robert, what do you calculate? Yeah, 22.5 divided by 560. 40.18. And the units were again? Current. What kind of amps? Milliamps. Everybody concur? Okay, so this is equal to my I2. Big step. We have a V2, we have an I2. So let's go ahead and put a box around it. We've just calculated it. And let's go ahead and continue. How do we calculate for V3? My hand is not working on the screen. This is going to be fun. Nope. Come on, go up. Okay, there it is. I got my hand working on it. All right. So I'm now going to be looking for an I3. So how do I find my V3? So Jacqueline, you were about to say?
14 over.
Give me the formula to set things up.
V1 over V3 equals N1 over N3.
Okay, so we're going to do a V1 over V3 equals N1 over N3. And when we go to fill the numbers in, as we did earlier, my V1 still stays as 120. V3 is our unknown. And my N1 is what value, Jacqueline?
N1 is 14.
N1 is 14. And
N3 is 5.
yeah, 14 over 5. Does everybody see where the 14 over 5 comes from? I have a pair of numbers on the bottom of the transformer. I have a pair of turns at the top of the transformer. The turns are different. Okay. And so now, as we go to solve this via cross multiplication, this works out to be 5 times 120. Works out to be 600 is equal to 14 times V3. And when we divide both sides by 14, my V3 works out to be what value?
42.86 volts.
42.86 volts RMS. Is everybody okay with that value? Okay, now we have solved for V3. Now let's go ahead and determine the current I3. So for I3, Yusuf, what are we going to do here? Okay, RL2. So V3 divided by RL2. Let me neaten that up a little bit. That looks horrible. V3 divided by RL2, and let's go ahead and pop in the numbers. V3, we had 42.86 VRMS, and we're going to divide by 470 ohms in this case. And Yusuf, what do you calculate for the current I3? 91.19 milliamps is equal to my I3. Does everybody concur on that?
Yes.
Okay. Now, everybody okay with the numbers I have outlined so far in green and red?
Yep.
So we have a V2 over here. V2 is equal to this. Put that in a box. I have an I2 as 40.18 milliamps. I have a V3 of this, and I have an I3 of this. Do we have enough information now to be able to calculate my P2 and my P3? Okay, so Sarah, help us out. How am I going to do a P2? Okay, And so P2 is going to be which current times which voltage? Mm-hmm. And the values of I2 we had as 40.18 milliamps. And this is going to multiply by V2 of 22.5 VRMS. And when we go to do this, enter times 22.5. What do you calculate for the power there? 904.05. I'm going to put down 0.02 milliwatts because I'm using all memories. So that's my P2. If you're within a hundredth of a decimal place of this, that's fine. 0.05 milliwatts works out great. Terrific. All right. And now for P3, Mr. Weiji, back to you.
So,
IV, which I times which V?
V3 times I3.
Okay. And my I3 is 91.19 milliamps. I'm going to multiply this by my V3 of 42.86 volts RMS. And
So we got
enter times. And what do you calculate for the power, sir?
3.91 volts.
Okay, works out to be 3.91 watts is equal to my P3. Okay. So now that you have P1, P2 and P3, how do we determine P1? The question goes to Jacqueline. What do you think? What are we going to do for P1? We said before, okay, let me put down here. Before, we said P1 is equal to P2, yes? That's with a single secondary. What do you think would happen here when we have multiple secondaries, as shown in this diagram here?
We have
Add
P2
them and then divide by 2.
Well, Well, let's go ahead and you're on the right track because we have multiple secondaries. So I'm going to do this now with multiple secondaries. P secondary is equal to P2 plus P3. Is that correct? Would that be an appropriate way to state my secondary power? To just call it SEC secondary? And that is equal to the sum of P1 plus P2 plus P3. So what's that work out to be, Jacqueline? P secondary. 904.02. Oh, that's horrible. I got my floating pen here. I'll fix that in a moment. 902.02 milliwatts. And we're going to add that to 3.91 watts. So I'm going to hit plus and that. And so what do you get?
9.94 watts?
Oh, no, I don't think so. It's 900 milliwatts. So it's less than 1 watt plus 4.91, 3.91. So it should be 4 point something.
Yeah. I had my milliwatts.
It's all right.
So 4.81.
4.81 watts equals P secondary. So we can't just name my secondary power P2 because we had 2 secondaries. So my entire secondary is just P sec, and that's 4.81. And how do I determine then my P1? Yeah, so P1 is your P secondary. So P1 is equal to 4.81 watts. Everybody okay with power of the primary? So how much current is running in the primary? Is the next question. How do I determine now I1 equals question mark? With I1, if you look at the original transformer formulas, let me scroll back up to the beginning. If you look at our original transformer formulas, we had I2 over I1 equals these ratios, I3 over I1 equals these ratios. We can't quite use these formulas to determine I1 because we have multiple secondaries. Does somebody have a guess as to how we determine I1? Use Watt's law. Watt's laws. And the most common Watt's law that we had used was P was equal to I V, yes? And so if we're looking for power of the primary, would it be okay that we say P1 is equal to I1 times V1? Is that right? Do we know P1? Did we just calculate P1? We did. We also have V1 was given. So how do I find I1? So I find I1 by doing this. If I divide both sides by V1, won't that give me I1? So what this works out to be, my friends, is this. I1 would be equal to P1 divided by V1. Power of the primary, we determine right here, 4.81 watts. And now divide by V1, which was given as 120 volts. So Sarah, what do you think here?
40.08 milliwatts.
And if I use all memories, yeah, we'd be very close. 40 point, I'll round out, 10 milliamps RMS equals I1. And if you're 40 point some decimal number and it's not exactly 0.10, it's okay. I'm just using more memory spaces and this is what we end up with. Are we okay with this so far? Everybody okay with how to handle a multiple secondary exercise? What happens if I put on 3 or 4 secondaries? It's just the same drill except 3-4 times, okay? So far so good? All right, okay. Now there's another exercise that I'd like to put forth to you and let you think about. Let me go ahead and find that. That will be here. And let's go here. It's part of this weekend's homework assignment. But I'm going to change a few things for us. It'll be transformer analysis number 3. Let that open up. Document. Okay, here we are, Word document. Make this bigger. And make this bigger. Okay, you see those waveforms? In a moment. In a moment. In a moment. There it is. All right, you see that pretty well on the screen?
Yeah.
All right. So you have an input waveform of 27 millivolts per division, and the waveform is at 85 microseconds per division. Then the output waveform is 1.0 volts per division at 85 microseconds per division. So now we're going to use waveforms that you're likely to read off of an oscope attached to the front end of the transformer and attached to the back end of the transformer. You need to determine how this transformer is behaving, all right? So let's go ahead and determine what the input waveform amplitude is. How do I determine my V peak, Yusuf?
It's 27 millivolts per vertical square.
Yeah, each vertical square, you're right, is 27 millivolts per division. So what do I do here?
You want to peak or peak? Sorry.
Yeah, so how do I determine my V peak?
27 times 3.
Okay, so it would be 3 divisions times 27 millivolts, yes? So everybody, let's go ahead and do that. So take 27 millivolts times 3, and Yusuf, you calculate what voltage peak on that?
81 millivolts.
Okay, so we calculate 81.00 milli V peak. Everybody all right with that? Okay. And then, let's go ahead and highlight that guy. Then our output waveform, how do we determine that particular guy? Wei-Ji, you're up.
So we got 1.6 division vertically, and then
Does everybody look at that closely? Does it look like 1.6 division?
Yeah.
So you look at the positive peak over here. The positive peaks are pretty far away from the center graduated line, right? But take a look at the negative peak. The negative peak is almost right on top of the center vertical line where the graduations are. And if you use the negative peak, because it's closest, almost on top of the center vertical axis, and look at the graduations, can you verify, do you concur with your classmate that this looks like to be 1.6 divisions?
Yeah.
Everybody okay with that? So what do we do with the 1.6 divisions, Yusuf?
multiply them by the number of volts per division.
Okay, actually that was Wei-Ji, right? Yeah, Wei-Ji, that's what we do, yes?
You will multiply by the 1 volt per division.
Okay, so what do you end up with the volts peak on that?
1.6. 1.6 volt.
1.60 capital V peak. Is everybody all right with those numbers so far?
Yeah.
Okay, now let's go highlight that. And then what else are we looking for? Is the voltage transformer above a voltage step up or a voltage step down transformer? Robert, what do you think? Well, look at the question that the next question, the third question says, is the transformer above a voltage step up or a voltage step down transformer? And it's a step up. How many people agree that this is a voltage step up? Raise your hands. Yep, it's a voltage step up. Why? Well, I need you to verbalize the why. Yeah, because the output voltage is bigger than the input voltage, yes? The output voltage is 1.6 volts, whereas the input is only in millivolts. So this would be a voltage step up transformer. Step up. It helps if I spell that correctly. It's hard typing with gloves. Step up. So far, so good. Okay, and now let me move this up. So if this is a voltage step up, then what happens to current? Jacqueline?
The current will go down.
Step down. Okay, voltage step down. We'll go ahead and do that here. Now, calculate the turns ratio. So the turns ratio, Sarah, this comes to you. How would I determine my turns ratio? We would use the transformer formulas. The transformer formulas I reiterated at the top of this paper. And so you can see an illustration of the transformer with an iron core. You can see windings on the primary. You can see windings on the secondary. And as we run AC through the primary, we're going to see something wonderful happen in the secondary. And we should be able to determine our turns ratio based on the information we have so far. So turns ratio was given as N1 over N2. So what are we gonna, how are we gonna set that up?
Who are you asking?
No, Sarah.
Or in two, do we use V1 over V2?
Precisely. V1 divided by V2, yes? So your N1 over N2 is equal to your V1 over V2. And so now we can fill in some numbers here. I can't write on this particular screen because I'm not in that application, but let's go ahead and do this. We happen to have my V1 0.081, and we're going to divide by 1.6. And what's that calculate to be? We can calculate this to a decimal. That would be equal to 81 milli-V divided by 1.6 V. And Sarah, what do you have?
50.63 milli ratio.
63. And then you could write it this way, 2, 1. Okay? You can write it milli. There's a milli in here, sorry. Milli. Yeah. So 50.63 milli to 1. Which is the same as saying, I can do this over here, equals 50.63 milli. Okay, you can also just leave it this way without the colon symbol. All right, now the next question, Yusuf, next question is, how do you determine your input waveform period? How do we do that?
Start of our waveform, the end of one cycle.
And what do you calculate in terms of number of divisions there?
85 micro.
Number of divisions. Yeah. How many divisions do you count?
I can't see that.
Here. Let me move this back down. And it should show us in a moment. Come on, be nice to me. It's that, oh, there it is. Okay. It's cooperating. Come on. It's almost there. We're really running a lot of resources here. I'll tell you what, let me turn off the Barco and let me turn the Barco back on. My desktop. There we go. All right. Now, so based on the waveforms, what do you see there? How many divisions do we count for one cycle, Yusuf?
5.
How many people agree we have 5 divisions horizontally for one cycle? And what do you do with those 5 divisions, Yusuf?
Multiply them by 85 nanoseconds.
Nano or what? What do we see there? Oh, okay, 5 times 85 microseconds. And so what is the period that you calculate, my friend?
425 microhertz. Microseconds.
Yes. So it would be 5
425.
times 85 microseconds equals, and you calculate 425 microseconds. Okay. How many people concur? Good. And I'll go ahead and highlight that. And therefore, what frequency do you calculate, sir?
2.35 kilohertz.
2.35 kilohertz. Everybody concur?
Yep.
All right. And it turns out if you do the, you look at the second waveform for the output, that information repeats here, paste, to be the same.
How do we get frequency again?
Is the reciprocal of your period. Yeah, you reciprocate. And so the last question here is, should or should not the frequencies be the same for input and output waveforms? Should, yes. Okay. Does everybody feel more comfortable with this exercise, having reviewed these waveforms and how to read them?
Yes.
Okay. Let me bring these guys back down. Gosh, it's really hard doing this with gloves. Okay, so I will go ahead and do a file save on this and pause our recording.